Hello and welcome. In this lecture we will apply Laplace transforms for solving linear time invariant ordinary differential equations that we commonly encounter in process control, process dynamics and control. Now the procedure for obtaining the time response output time response to a forcing function for a linear time invariant ordinary differential equation consists of first Laplace transforming the ODE, and when you Laplace transform the ODE, if the initial conditions are 0, then all you do is you simply replace the nth derivative with s to the power n, and the forcing function u is usually given to you, so the Laplace transform of the forcing function is known, and therefore you can get, in this way you can get an expression for ys, and this expression will be, for example, of this form, where the forcing function, this form is for a forcing function for a unit step where u of s is 1 by s, so I've multiplied by s all the terms in the denominator of the transfer function. What I'm trying to say is, if y of s by u of s, which is the transfer function, is summation aj s to the power j divided by summation b I s to the power I, this goes till m, this goes till n is greater than or equal to m, then y sub s will be g times u of s, and u of s, if it's a unit step, it's going to be summation aj s to the power j divided by summation bi s to the power, I think I plus 1, because you're multiplying by s, I equal to 1 to n. Yeah, so that's what this is. So you have an expression for y of s, and once you have an expression for y of s, you factorize the denominator into its factors. So if it's a polynomial of order n plus 1, there will be n plus 1 factors, and once you have these n plus 1 factors and the denominator has been factorized into the product of its factors, n plus 1 factors, then what you do is use partial fractions to express ys as a sum of known transforms. And what are the known transforms? For example, s plus lambda 1, I've given you an example here. So s equal to 0, s equal to minus lambda 1, s equal to minus lambda 2, s equal to minus lambda 3 repeated twice, and so on and so forth. These are the factors, and so using partial fractions you can say that this expression is the same as this expression, and I know the Laplace transform of this. This is the Laplace transform of 1. This is the Laplace transform of e to the power minus lambda 1 t. This is the Laplace transform of e to the power minus lambda 2 t. This is the Laplace transform of e to the power minus lambda 3 t, and this square is the Laplace transform of t e to the power minus lambda 3 t, and so on and so forth. So you factorize the denominator and use partial fractions to express ys as a sum of known transform, and then you use these known transforms to obtain yt as, you know. So this is the basic procedure, and now we will apply this procedure to solve some very simple equations. First order ODE. Well, for a unit step function, we will have the Laplace transform. If you do the Laplace transform of both sides, you'll have tau s y of s plus y of s, and therefore what you get is so this is the transfer function y to u, and if u of s is a unit step, then u of s, if u is a unit step, then u of s is 1 by s, and therefore what you get is y of s is equal to k upon s times tau s plus 1. And the most convenient way of using partial fractions is to have the highest power of s in any factor, you know, that coefficient to be 1. So what we will do is we will say, okay, so y sub s is equal to, take tau common, and you will get k by tau into 1 over s plus 1 by tau, and I'll call that this is equal to k by tau times f of s, where I'm calling 1 over s times s plus 1 by tau as f of s. And then you can see that f of s can be expressed as a sum of partial functions a by partial fractions a by s plus b by s plus 1 by tau. And if you want to obtain a, maybe I should just do it a bit more detailed so that things are clear to you. So f of s is equal to 1 over s times s plus 1 by tau. Okay, so now if I want to calculate a, multiply both sides by s. So if you multiply both sides by s, what you will get is 1 over s plus 1 by tau is equal to a plus bs over s plus 1 by tau. And now if you substitute s equal to 0, then you will see that this goes to 0 for s equal to 0, and then you get a is equal to, so put s equal to 0, and so then you get a is equal to 1 over 1 by tau, which is tau. Yeah, so basically how did we get a? We got a by saying that a is equal to s times f of s calculated at s equal to 0, and this gives us a is equal to 1 by tau. Similarly, how will we get b? We'll get b is equal to s plus 1 by tau times f of s calculated at s is equal to minus 1 by tau, and this would give, oh sorry, this is wrong, this gave us a is equal to tau. This will give us, so if you look at f of s, this part goes and you're left with 1 by s, and put s is equal to minus 1 by tau, So you'll get b is equal to minus tau. And therefore y sub s is equal to k by tau multiplied by tau by s minus tau over s plus 1 by tau. And so what you get is, this is, the tau will cancel out, so you'll get y sub s is equal to k times 1 by s minus 1 over s plus 1 by tau. And now if you take, this is the Laplace transform of unit step, this is the Laplace transform of e to the power minus t by tau, and therefore y of t inverse Laplace transforming y of t going back to the time domain, you get is equal to k times 1 minus e to the power minus t by tau. So using Laplace transforms we easily obtain, and so the procedure summarized: Laplace transform, is the Laplace transform the transfer function, substitute us equal to 1 by s, which is the Laplace transform of the unit step, because the system is forced by a unit step, so u of s is equal to 1 by s, and this gives you this guy, and using partial fractions you get y of s is equal to this, and therefore y of t is equal to, now if you look at this response and if you plot this response, this is u and this is y, and you can see that u changes by 1, the total change in the output is by k, and in one time constant 63.2% of the distance gets traveled. In two time constants 86.5% of the distance gets traveled, and in three time constants 95% of the response completes. So these are the characteristics of a first order ODE, a first order lag with gain k, and first order log is very commonly employed. By default, if you say first order lag and do not specify the gain, that means the gain is 1. Okay. Now let's look at a second order ODE. The general form of a second order ODE is in front of you. Zero initial conditions forced by a unit step, and so let's take the case of we'll take critically damped first, and then we'll take the overdamped case. So critically damped means epsilon or the damping coefficient chi is equal to 1. Sorry, I write chi as epsilon because that's just by habit. I'm not very good with curves. Yeah, okay, so so in that case your governing differential equation is, well, if you take the Laplace transform of both sides, you'll get tau square s square plus 2 plus 1 applied on y of s must be equal to k times u of s, and we are saying 2 epsilon tau, sorry, and we are saying this epsilon is going to 1. So therefore what we get is, for a unit step, u of s is equal to 1 by s, so y sub s will be k divided by tau square s square plus 2 tau s plus 1 times s, and therefore what you get then is y sub s is equal to k by tau square. Make the highest coefficient 1, take tau square common, so 1 by s times s square plus 2 by tau s plus 1 by tau square, and you can see by inspection this guy is nothing but the square of s plus 1 by tau. So therefore what we get is y sub s is equal to k by tau square into 1 by s times s plus 1 by tau whole square. And now we want the partial fractions, so we'll say is equal to k by tau square times f of s, where f of s is the guy in the square brackets. So now we say okay, f of s is equal to 1 by s into s plus 1 by tau whole square, and by partial fractions this guy is going to be a by s plus b by s plus 1 by tau plus c by s plus 1 by tau whole square. And how do we get a? Well, a, a is equal to s times f of s calculated at s equal to 0, and this gives a is equal to tau square. How do we get b? B gets tricky because you got the same factors. So if you multiply by s plus 1 by tau whole square, so let's see how we get c. So in order to get c, multiply by s plus 1 by tau whole square both sides, and so what you will get is s plus 1 by tau whole square times f of s is going to be equal to a by s times s plus 1 by tau whole square plus b times s plus 1 by tau plus c. And you can see that if I put s is equal to minus 1 by tau, so if I put s is equal to minus 1 by tau, for s is equal to minus 1 by tau, these terms disappear, and on the right hand side you are left with c. On the left hand side you are left with 1 by s, because this times f of s, s plus 1 by tau square, s plus 1 by tau square cancel out, you are left with 1 by s, and so you put s is equal to minus 1 by tau, that is equal to c. So c is obtained the usual way. C is equal to s plus 1 by tau whole square f of s calculated at s is equal to minus 1 by tau. So that's how you obtain c, and so what you get from this is c is equal to minus 1 by tau. Now in this equation, if you look at this equation again, by multiplying, let us say I differentiate this equation once with respect to s. So if I differentiate this equation once with respect to s, then what I get is derivative with respect to s of s plus 1 by tau whole square f of s is going to be a times s plus 1 by tau whole square times 1 by s square with a negative sign there, so that's what this is going to be, minus plus a by s times derivative of s plus 1 by tau whole square, which is going to be 2 times s plus 1 by tau, plus b, derivative with respect to s of c is, which is a constant, is going to be 0. And so you can see that this guy is actually s plus 1 by tau taken common times minus, in fact with a, times minus 1 by s square times s plus 1 by tau plus 2 by s plus b. Now if I put s is equal to minus 1 by tau on both sides of this equation, then this term disappears, so the a term disappears and you're left with b. So what I get is b is equal to d by ds of s plus 1 by tau whole square f of s calculated at s is equal to minus 1 by tau. That's what b is, and if you do that, s plus 1 by tau whole square times fs is actually 1 by s, derivative of that is minus 1 by s square calculated at s is equal to minus 1 by tau, which implies that b is equal to minus tau square. Yeah. So this is what we have gotten. We've gotten a is equal to tau square, b is equal to minus tau. Isn't that what we got? Shucks, where did we get c? I don't remember. No, b is equal to minus tau square and c is equal to minus tau. I think that's what we got. And so what we have finally gotten is that y sub s turns out to be, and therefore y sub s turns out to be k by tau square into tau square by s minus tau square by s plus 1 by tau minus tau by s plus 1 by tau whole square. And we know the inverse Laplace transforms of all this, so you know that's equal to k by, that's actually equal to k times 1 by s minus 1 by s plus 1 by tau minus 1 by tau times 1 by s plus 1 by tau whole square. And if we take the inverse, if we go back to the time domain, what we then get is that, going back to the time domain, what we then get is that y of t is equal to k times, this is 1 minus e to the power minus 1 by tau, or times t, which is minus t by tau, minus minus t by tau times e to the power minus t by tau again, and this implies y as a function of time is k times 1 minus 1 plus t by tau times e to the power minus t by tau. So this is the expression that I get for an overdamped system by using Laplace transforms. Let's look at for a critically damped system, sorry, where epsilon is or where the damping coefficient chi is 1. Let's look at an overdamped system where chi is greater than 1. So if you look at an overdamped system, then what we have is that y sub s for the overdamped case, we have y sub s is equal to k by tau square into 1 over s plus 2 s square epsilon by tau s plus 1 by tau square into s. Okay, so this is a quadratic, and for epsilon greater than 1 the roots are, if you want to factorize this, the roots are s is equal to minus epsilon by tau plus minus square root epsilon square minus 1 divided by tau. So these are the two roots of this equation, and let me call lambda 1 is equal to minus, or lambda 1 is equal to plus epsilon by tau, minus square root epsilon square minus 1 by tau, and let me call lambda 2 is equal to epsilon by tau plus square root epsilon square minus 1 by tau, and in that case y sub s turns out to be k by tau square into 1 by s times s plus lambda 1 into s plus lambda 2. Now that being the case, partial fractions, again I'll say fs is equal to 1 over s times s plus lambda 1 into s plus lambda 2 is equal to a by s plus b by s plus lambda 1 plus c by s plus lambda 2. By the way, if I look at lambda 1 times lambda 2, and you can see if you multiply, then it will be epsilon by tau whole square minus, it will be this square minus this square. Yeah, so if you do that, the epsilon square by tau square terms will cancel out, and what you will be left with what will you be left with? Arey yaar, what will you be left with? It will be minus minus, so it will be 1 by tau square. Yeah. So lambda square, lambda 1, lambda 2 is actually 1 by tau square. So if I look at it in terms of lambda 1, lambda 2, this is actually k times lambda 1, lambda 2. Yeah. Okay. Let's get A, B and C. As usual, A turns out to be, you hide s equal to 0. So A will be s times fs calculated at s equal to 0, and this implies that A is equal to 1 by lambda 1, lambda 2. Now let's look at B. B is going to be s plus lambda 1 times fs calculated at s is equal to minus lambda 1. And what does this give B as? So B is equal to, so hide this guy, minus lambda 1 times lambda 2 minus lambda 1. So this will be minus 1 over lambda 1 into lambda 2 minus lambda 1. And similarly, C is going to be s plus lambda 2 times f of s calculated at s is equal to minus lambda 2. This implies C is equal to plus 1 over lambda 2 multiplied by lambda 2 minus lambda 1, and thus you get y sub s is equal to k times lambda 1, lambda 2 times 1 by lambda 1, lambda 2 times 1 by s minus 1 by lambda 1 into lambda 2 minus lambda 1 times 1 by s plus lambda 1, and this is plus 1 by lambda 2 into lambda 2 minus lambda 1 times 1 over s plus lambda 2. Okay, and multiply by lambda 1, lambda 2, so you get y sub s is equal to k times 1 by s minus lambda 2 by lambda 2 minus lambda 1 times 1 over s plus lambda 1 plus lambda 1 over lambda 2 minus lambda 1 into 1 over s plus lambda 2. And once you have that, you know the inverse Laplace transform of this, you know the inverse Laplace transform of this, or rather you know 1 by s is the Laplace transform of 1. 1 by s plus lambda 1 is the Laplace transform of e to the power minus lambda 1 t, and 1 by s plus lambda 2 is the Laplace transform of e to the power minus lambda 2 t. So therefore y of t, maybe I should write it here, therefore y of t is going to be k times 1 minus lambda 2 upon lambda 2 minus lambda 1 e to the power minus lambda 1 t plus lambda 1 upon lambda 2 minus lambda 1 times e to the power minus lambda 2 t. So using Laplace transforms, we've solved this second order overdamped differential equation to obtain our solution, analytical solution, the analytical expression for y of t. Having done this, I'll quickly summarize. For the overdamped case, taking Laplace transform of both sides, this is what we get. Substitute us is equal to 1 by s. Of course, this is the transfer function. Substitute us equal to 1 by s. This is what you get. Use partial fractions to factorize as above, and using partial fractions, this is what we get, and this gives us y of t as noted here. For the overdamped case, procedure is the same. It's just that this is a perfect square. Because this is a perfect square, you get this and make the coefficient of s square 1, and using partial fractions, that's what we get, and final expression for y of t is as noted here. This is what we derived. Now let's look at the most interesting case where epsilon is between, or the damping coefficient. By the way, this chi is also called the damping coefficient. Maybe I forgot this, but damping coefficient. The damping coefficient is between 0 and 1, and if the damping coefficient is between 0 and 1, everything is the same except that now the roots become complex conjugate pairs. So what you get is as before, y sub s is going to be k by tau square into 1 over s times s times s plus s square plus 2 epsilon by tau plus 1 by tau square, and this guy has as its roots s is equal to minus epsilon by tau plus minus square root of 1 minus epsilon square times j divided by tau. So these are your two roots, and therefore y of s, we'll call this as k times f of s, and therefore f of s, which is equal to 1 over s times s square plus 2 epsilon by tau s plus 1 by tau square is equal to 1 over s times s plus, let's take the plus root first, s plus epsilon by tau minus square root 1 minus epsilon square by tau times s plus epsilon by tau, there's a j that I missed, plus j times square root 1 minus epsilon square by tau. And by partial fractions, we are going to say that this is equal to a by s plus b by s plus epsilon by tau minus j times square root epsilon square minus 1 by tau plus c by s plus epsilon by tau plus j times square root. अरे यार ये गड़बड़ कर दिया, sorry. This must be 1 minus epsilon square because epsilon is less than 1. Yeah, so 1 minus chi square by tau. And as usual we obtain a as equal to tau square, s times fs calculated at s equal to 0. B, let us see what B is going to turn out to be. If you want B, then you remove this guy because you multiplied by that guy and then substitute s is equal to, okay, so B is going to be calculated as s plus epsilon by tau minus j times square root 1 minus epsilon square by tau times f of s. This thing calculated at s is equal to minus epsilon by tau plus j square root 1 minus epsilon square by tau. So if you do this, this will give us that actually B is equal to, let's see, 1 over minus epsilon by tau plus j times square root 1 minus epsilon square by tau, that's the s term, and then from this term what we get is minus epsilon by tau plus epsilon by tau cancels out, you get 2 times j times square root 1 minus epsilon square by tau, which implies that B is equal to tau square by two j times square root 1 minus epsilon square times minus epsilon plus j times, okay, so that's B. And if you want C, you can do the same thing, but C can be simply obtained by replacing j with minus j because the root is a complex conjugate. So just replace j with minus j and what you will get is C is equal to tau square divided by minus 2j into square root 1 minus epsilon square into minus epsilon minus j divided by square root 1 minus epsilon square, and this minus you can take in and this becomes, so now I think I'm running out of space here, so let's see, so let's create some space. So A, B and C have been calculated using partial fractions, and therefore y sub s will turn out to be k times 1 by s plus I mean between the coefficients this factor is common, so we'll take it common, Okay, so let's take it common. So we'll say okay, 1 by 2j into square root 1 minus epsilon square, and then we have 1 over minus epsilon plus j times square root 1 minus epsilon square into 1 over s plus epsilon by tau minus j times square root 1 minus epsilon square by tau plus 1 over epsilon plus j times square root 1 minus 1 square into 1 over s plus epsilon by tau plus j times square root 1 minus epsilon square by tau. Close the brackets. Okay, now that we've got y sub s, let's look at this complex number, these two complex numbers. If I multiply by their complex conjugate, what I will get is epsilon square minus j square times square root 1 minus epsilon square. So that's going to be epsilon square minus plus 1 minus epsilon square, that is equal to 1. So both these complex numbers, this one and this one, are magnitude 1, and so that's that. We can further simplify or further, say that okay, this is equal to k times 1 by s plus 1 by 2j into square root 1 minus epsilon square into this would be minus epsilon minus j times square root 1 minus, actually it's not epsilon, chi square. This minus I can, let me make this minus, and then this will be plus and plus, and the denominator is going to be s plus chi by tau minus j times square root 1 minus chi square divided by tau. And over here I'll keep the sign waiting. We'll figure out the sign in just a little bit. This remains. And on top we will get epsilon minus j times square root 1 minus chi square, and because I already have a negative sign here, I must put a negative sign here, and then it shall be correct. Okay, very good. Now let's go back to the time domain, and when you go back to the time domain, 1 by s is the Laplace transform of 1. The other Laplace transforms have a real part and a complex part. The real part is negative, the complex part exists in conjugates, and that will always be the case. Transfer functions will have real coefficients, so any complex roots will have to necessarily occur in complex conjugate pairs. Okay, only then will you get all real coefficients. Okay, so let's look at this guy. Y of t therefore will turn out to be k times 1 minus 1 by 2j square root 1 minus. By the way, let's look at this complex number again. And real axis, imaginary axis, and let this guy be. So then this complex number is, so the complex number in polar form has an angle phi and a magnitude 1. So I can say that chi plus j times square root 1 minus chi square is actually equal to 1 times e to the power j phi in polar form, where phi is equal to cos inverse chi. It's also equal to sine inverse square root 1 minus chi square. It's also equal to tan inverse square root 1 minus chi square divided by chi. Alright, if that is this number, then the other number which is here, which is this chap, this number is, it's just a complex conjugate, and therefore all you do is 1 times e to the power minus j phi. Yeah, and so we will have, put in your curly brackets, e to the power j phi times, when you go invert this Laplace transform, it will be e to the power minus epsilon by tau plus j times square root 1 minus chi square by tau, this whole thing times t, minus e to the power minus j phi times e to the power minus epsilon by tau minus j times square root 1 minus chi square divided by tau, whole thing times t. That is what we have, and you can see where we are headed. Let's take the 2j inside. And let's take the e to the power minus epsilon by tau times t, which is common to both terms, outside, and so what we get is y at time t is equal to k times 1 minus e to the power minus epsilon by tau times t divided by square root 1 minus chi square times e to the power j times square root 1 minus chi square by tau times t plus phi minus e to the power minus j times, and you will get again square root 1 minus chi square by tau times t plus phi, and the whole thing is divided by 2j. And you can see that from the Euler identities, this is nothing but sine of the thing that occurs in the square brackets. So therefore eventually what you get is that y of t is equal to k times 1 minus e to the power minus by tau t divided by square root 1 minus chi square times sine of square root 1 minus chi square by tau times t plus phi. So this is my analytical solution for the time evolution of y, and phi of course is given by phi is given by this guy. Yeah, so that's my solution, and I'll just quickly walk you over how we went through all this. So we got an expression for y sub s, factorized it, and then using partial fractions we got the expressions for a, b and c, and once we got the expressions for a, b and c, we substituted them, and that's what we got. Went to the time domain, and once all the algebra got done, we essentially got what we got. Okay, so the second order underdamped, you can see from the expression, if epsilon is, or if chi is between 0 and 1, this number is positive. If this number is positive, in time it will decay to 0, and then you have this decaying to 0 number multiplied by a sign which oscillates between -1 and +1. So you can see that the response will look, and the final value, if you take this to 0, final value is going to be k. So you can see that the response will look, its shape is going to be, if you give it a small step, unit step, response is going to go to k, but it's going to go to k in an oscillating manner. It's going to go to k and this envelope is e to the power minus chi by tau t. That's the kind of response that you expect. And what I did was, so we've looked at overdamped, critically damped and underdamped. So what I did was I just took a system and got its response as chi was varied from a large value, that means highly underdamped or highly overdamped, and I kept reducing chi from 6 to 3 to 1.5 to 1. This is critically damped. Underdamped 0.25, and you can see this is what you got when you have chi equal to 6. This is what you get when you have chi equal to 3. This is what you get when you have chi equal to 1.5. This is the critically damped response. For chi equal to 0.5, this is what you get, and for chi is equal to 0.25, this is what you get. And for comparison, I have also drawn a first order response, that's this guy, first order, with a time constant tau. And you can see the first order is actually the fastest, second order is slower. Second order can have oscillations if you have underdamped system, and as the damping coefficient decreases, the response becomes faster and faster and faster. Yeah, however, as you become too fast, the critical damping case is the case where you get no sine term. So non-oscillatory response. After uh, chi goes below 1, you start getting the sine term in yt, and that is the source of these oscillations. Well, I guess that's all that I wanted to say. Okay, now if you look at the second order underdamped unit step response, it has some characteristics, and these characteristics are used a lot in the design of controllers, and it is used in the design of controllers because as you change the gain, at a very low gain you have a highly overdamped system, so chi is much greater than 1. As you start cranking up the gain, the proportional gain in a PID controller, chi starts to reduce. Keep cranking up the gain, chi reduces further, it reaches 1, and then it goes below 1. In fact, if you keep cranking up the gain, you may even have chi reach 0, in which case hang on so in which case, if you look at, if chi is 0, you'll get a pure, this term goes to 1, and you'll get a pure sinusoid, you get sustained oscillations. Now if chi goes less than 0, then this term is going to blow up, and then you'll get oscillations that blow up. Yeah, so in control systems, an underdamped response, slightly oscillatory response, is what you often target, and therefore it is good to know the characteristics and have some metrics to quantify the characteristics of an underdamped response. And some of these characteristics are: the first time, so final value is going to be k, let us say. The first time you hit k, that's called the rise time. This is the rise time. The time it takes for the response to reach its first peak, that's called the peak time. Now you can see the response overshoots the final value by an amount a. So a by k is called the peak overshoot ratio. What percentage overshoot we have compared to the total response? How much do you overshoot the response by? The percentage overshoot is called peak overshoot ratio. You get a second peak, and of course the second peak is not as large as the first peak, so the second peak is b, first peak is a. B by a is called the decay ratio, and you would like a good decay ratio, at least 4, preferably more, maybe something like 6 or 8. Okay, and then you have the f% settling time. You got a sine wave, and this sine wave is being multiplied by e to the power minus epsilon by tau times t. The sine wave is always going to keep oscillating between 0 and 1. It is this number, if this reduces sufficiently to say f% of k, so that will be f by 100 times k, because k is the total response, f% within k. So what that means is, if this guy reduces to f% within k, f% of k, then what that means is that the oscillations are always going to be bounded beyond that time within f%. So this is called the f% settling time. Of course, f% settling time. Okay, so now and these characteristics are related to chi, your damping coefficient chi. And so I have given you these expressions, and I think this is one of the assignments also, derive these things. Maybe I should derive it now for your benefit. So y of t is k times 1 minus e to the power minus epsilon by tau times t divided by square root 1 minus chi square times sine square root 1 minus chi square by tau times t plus phi. Alright, rise time corresponds to that time when response becomes equal to k for the first time. What that means is the sine term here must go to 0 for the first time. That means sine square root 1 minus chi square by tau times t plus phi goes to 0 first time. Note that at time t equal to 0, phi is a positive number. Because phi is a positive number and t equal to 0, so sine starts from the angle in the sine term starts from not 0 but a number that is greater than 0, say 45 degrees or something like that. So the first time that you're going to hit 0 after time t equal to 0 is going to be when the sine reaches pi, when the angle in the sine reaches pi. So what that means is square root 1 minus by tau times rise time plus phi must become equal to pi, and what that does is tells us that rise time is equal to pi minus phi divided by square root 1 minus chi square, but square root 1 minus chi square is actually sine phi. So that takes care of this guy. Now let's look at the peak time. At the peak, the derivative disappears. The derivative of y with respect to time disappears. So let us differentiate. So let's differentiate dy by dt. Differentiating both sides, what you get is minus k times, oh man, there are going to be two terms, okay, and we're going to put it equal to 0, but it's okay, minus k by square root 1 minus chi square times, okay, so now let's start differentiating. Derivative of sine is going to be e to the power, this term is going to be there. Derivative of sine is going to be cos of and this will get multiplied by derivative of the exponential term is going to be negative, and e to the power minus by tau t times sine of the same thing times and actually I can take this guy common. This is common to everything, so we'll take this as common and multiply this by. Now at the peak, this derivative must disappear, and this must disappear for the first time with a positive t. For this derivative to disappear, whatever is inside the square parentheses must disappear. So what I then have is, अबे ये क्या किया, इसकी जरूरत नहीं है, sorry, this one is not there. So for this thing to happen, the what is in the square parentheses must disappear, and what that means is, acha, by the way, tau also cancels out, so we'll take tau also out of the, just take tau also out of the, okay. So now what that means is, what we are saying is, and let's take the negative sign inside, so that will also, okay. So what that means now is that sine of that big angle times cos phi is actually chi minus cos of that big angle, and square root 1 minus chi square is actually sin phi. This must be 0. When will this go to 0? So this is actually sine that big angle. Big angle is, you know, that big expression angle, by tau t plus phi minus phi. So phi and phi cancel out, and therefore this guy must be equal to 0 for a peak or an, you know, or an undershoot. And this will go to 0 for the first time when you get the first peak, and at that point in time the angle must be pi. When the angle goes to 2 pi, it goes to 0 again, and at that point in time you are here. When the angle goes to 3 pi, then you are here. Angle goes to 4 pi, then you are here. So you'll get peaks corresponding to odd multiples of pi. You'll get undershoots corresponding to even multiples of pi. So therefore, for the peak, what we have is, for the first peak, by tau times first peak, that's going to be equal to pi, and therefore peak time is going to be pi by square root 1 minus chi square, which is sin phi. And the second peak, I'll call it TP2. The time corresponding to this guy is going to be 3 pi by sin phi. So once we have this, now we can start calculating. So at this point in time, what is y? So let's look at the first peak, at the time at which the first peak occurs. We know the value of the time. Now let us obtain what is the absolute value of y, and the absolute value of y is going to be so absolute value of y at peak time, at the first peak, so y at the first peak is going to be k times 1 minus e to the power, by the way, Tp by tau is pi by sin phi, and chi is actually cos phi, minus cos phi, and Tp by tau is actually pi by sin phi, so pi by sin phi times sine of essentially sin phi times Tp by tau, which is pi by sin phi, plus phi, and so that is going to be k times 1 plus, see, this cancels, and sin phi pi plus phi is minus sine phi. So this is going to be e to the power minus cot phi. Well, let's need to do a bit of a change. Minus pi times cot phi times sine phi. Is this correct? Am I doing the right thing? I thought the sine would have gone to 1. We'll see. Maybe I made a mistake. We'll find out. And so A by k, which is y peak minus k divided by k. So therefore A by k is going to be e to the power minus pi cot phi times sine phi. Okay, so that's the peak overshoot ratio. Let me see if I got the right expression. Maybe I made a mistake here, eh? I made a mistake. Okay, well, let's see what the mistake is. अरे यार सब गड़बड़ कर दिया और यार सब मिटा दिया. Okay, fine. Yt is equal to k times 1 minus e to the power minus y tau times t divided by divided by sine phi was missed. Okay, divided by sine phi times sine phi is what we would have gotten. So this cancels out, and so what you get is peak overshoot ratio. Yeah, okay, so I understand the mistake. The mistake was I missed this divide by sine phi in the derivation till now. So just rewind and see where we were and overlook. So peak over ratio actually turns out to be e to the power minus pi cot phi. Now if you look at the second peak, peak overshoot ratio for the second peak is going to be e to the power because now this one is going to be 3 pi. And the ratio of the two is going to be, which is decay ratio, which is equal to POR2 by POR3. Why did the pi come here? Because the angle became equal to pi for the first time. That corresponded to this guy. Angle becomes equal to 3 pi for the first time, corresponds to this one, and therefore, POR, and therefore this turns out to be e to the power minus 2 pi cot phi. So you can see we've derived this, we've also derived this, we've derived this. The last guy that is left is this guy. Settling time. Settling time is actually pretty straightforward. We have y of t is equal to k times 1 minus e to the power minus chi by tau t divided by square root 1 minus chi square into sine of square root 1 minus chi square by tau times t plus phi. Now for the oscillations to dampen to such an extent that the response oscillates between f% of the final value, which is k, what that then means is that this guy must decay to, well, this guy or this guy, the entire guy. Yeah, the entire guy. The multiplier of the sine must decay sufficiently what should be the time. settling time, such that this number is f% of k. So f by 100 times k. And then what you do is, take this to the right hand side. And then what you do is take the logarithm or natural log of both sides, and then what you get is minus ts by tau times chi is equal to ln, and this minus can be taken out here, f by 100 times k times sine phi, and this is cos phi, and so what you get is ts by tau is equal to well, what is it equal to? The inverse of what is inside the ln. So ln 100 by f k sine phi divided by cos phi. Yeah, so that's what looks like to me. Yeah, that's what it is. Hang on. Okay, so that's what it is. So we've derived all these metrics. So the point is, you see, phi is a function of chi, and if you are specifying the rise time, indirectly you're specifying phi, and if you're specifying phi, indirectly you're specifying the level of underdamping chi. So in controls, what you often do is you say, okay, design a controller so that the peak overshoot ratio is 10%. Peak overshoot ratio of 10% implies, so if I put peak over, so 0.1 equal to e to the power minus pi cot phi, this will imply phi, which in turn will imply chi, and like I said, chi depends on kc. As you change kc, chi changes, so now you calculate that value of chi for which you get the desired value of, you obtain that value of kc for which you get the desired value of chi. So any one of these specifications, decay ratio, peak overshoot ratio, peak time, rise time, settling time, is indirectly specifying what your chi should be. Okay. Now, just to emphasize, if chi is less than or equal to 0, then you can see if this is 0, this goes to 1. No, it goes to 1. If this goes to 1, then you get a pure sinusoid, you get sustained oscillations. On the other hand, if chi goes to less than 0, on the other hand, if chi is less than 0, then this term is positive, and if this term is positive, as time increases, this guy is going to keep going up and up and up. So you have the exponential term that's blowing up, and we are multiplying it by a sine wave, so you'll get oscillations that blow up. Yeah. So that's what you get here, and just to show you, for the system that we have been studying, this corresponds to chi equal to 0. The red curve corresponds to chi is equal to very slightly negative and minus 0.01, and you can see that the red curve is oscillations that are slowly blowing up in time. That's an unstable system. Like I said before, why are we so much interested in the second order system, underdamped system? It's because the controller gain affects the damping coefficient. Typically, as the gain is increased, the damping coefficient decreases, and it keeps on decreasing. And for real systems which are third order or more, why are they third order or more? Because the process itself must be at least a lag, the control valve will be at least a lag, the sensor also will be at least a lag. So that's a third order system at least. Okay, for systems that are third order or more, if you crank up Kc sufficiently high, you will start getting sustained oscillations. Your chi will go to 0. If you crank up the gain further higher than that, then you'll get oscillations that blow up, implying that chi has gone negative. So we are interested in that limiting value of Kc for which you get sustained oscillations, that is chi equal to 0. Any higher Kc will cause the oscillations to blow up, that is an unstable system. And so you tune controllers for Kc to be sufficiently away from the instability limit. I would say, this is on the higher side, 0.3 to 0.5. Typically, Kc is adjusted so that the closed loop damping coefficient is in the range 0.3 to 0.5. Now let's just describe you some exercises. So here's a lead lag. Okay, so obtain a transfer function relating y to u. Obtain the unit step response for this system using Laplace transforms, and sketch the unit step response for alpha greater than beta and alpha less than beta. And in the previous lecture I had shown you the lead lag. This is actually the lead lag, and once you obtain the analytical expressions for y of t, you should be able to see why the response is the way it was in the previous lecture. That's exercise 1. Exercise 2. Actually, exercise 2 can be done in the time domain, where you don't invoke Laplace transform and just derive the differential equations and solve them. It could also be done in the Laplace transform domain. So consider a process system which is actually a second order system with distinct roots. The distinct roots are s equal to minus 1 by tau 1 and s equal to minus 1 by tau 2. Okay, so if you look at the system, the system is actually, if you look at it in block diagram format, this is yu, and there's an ODE that relates, and this is disturbance. You add the two and you get y. And if you want the transfer function of this guy, the transfer function is going to be what? It's kp times, so it's kp divided by tau 1 tau 2 s square plus tau 1 plus tau 2 s plus 1. That's the transfer function, and d is simply a multiplying by a gain. So this is your system that you're looking at. Now u is adjusted to hold y by a p only controller. So you take y, subtract it out, you get the error signal multiplied by kc. That's your p controller. This is the set point. Now what you're supposed to do is obtain for this closed loop system, obtain the servo and regulator transfer functions, obtain controller gain Kc for a closed loop damping coefficient of 0.7071, and 0.7071 means chi is equal to 1 by square root 2, and therefore the angle phi that you're looking at is actually 45 degrees. 45 degrees means you're wanting a Kc for which the closed loop roots of the characteristic equation, and the characteristic equation is going to be second order because the transfer function is second order. The closed loop roots, the roots of the closed loop characteristic equation are such that the real part and the imaginary part are what shall we say, equal, and we are interested in that root for which the so they are equal. That's it. That's what we are interested in. So obtain the controller gain Kc for which chi is equal to 0.7071, which in other words means that the roots of the closed loop characteristic equation, which is second order, so it will have two roots. Those two roots are such that the real part and the imaginary part are of equal magnitude, because phi turns out to be 45 degrees. Plot the variation in the closed loop characteristic equation roots as Kc is increased from 0 to infinity. Once you have the expression for the closed loop characteristic equation roots, you can sort of think in your own mind as to how these roots are going to move as Kc is changed from 0 to infinity, and then make that sketch. Okay, so this is exercise 2. With this we come to the end of this rather long lecture. Maybe I should have split it into smaller ones, but maybe next semester that's what I'll do. So in summary, what we have seen is that Laplace transforms provide a convenient method for solving linear time invariant ODEs. And how we do that is we first Laplace transform the ODE for a given forcing function and obtain y of s. Then we use partial fractions to express y of s as a sum of known transforms, and then we since we know that y of s, since we know the transforms, the time functions from which these transforms are coming, we invert using these known transforms to obtain y of t. We looked at in detail the first order response. The key takeaway is it completes 63.2% in one time constant. Second order response can be overdamped, in which case you have distinct real roots or factors, distinct real roots of the characteristic equation, or distinct real factors of the polynomial in S in the denominator of the transfer function. You also have possible that you could have critically damped response, in which case the factors are real and repeated. That means the roots are repeated twice. Underdamped means you got complex conjugate roots, or the factors are complex conjugates of each other, and that's that. Overdamped response is sluggish. Critically damped response is the fastest response without any oscillations. Underdamped response will give you some oscillations, and these oscillations get more and more visible as chi decreases and approaches 0. At chi equal to 0, at a damping coefficient of 0, you get sustained oscillations. If the damping coefficient goes negative, you get oscillations that blow up. For a control loop, it is usually observed that as Kc is increased, the critical roots of the characteristic equation, they move from overdamped as Kc is increased to underdamped. So initially you get very smooth responses, then as you crank up the Kc, then you start getting some oscillations. That's a sign that you have underdamping. And then as you crank up Kc further, you may get oscillations that take very long to die out. That means chi is approaching 0. And then as you crank up Kc further, you get oscillations that don't die, sustained oscillations. That means chi is 0. And then if you crank up the gain further, then you get oscillations that blow up, and then you get an unstable system. So as Kc is increased, the roots of the characteristic equation which govern the response, at least some of those roots move from overdamped to underdamped to unstable. And it is this stability limit that we need to keep away from, and it is this stability limit that governs the tuning of our controller. And we are going to talk a lot about this in subsequent lectures. So with this we come to the end of this rather longish lecture. Thank you for your attention. Hope to see you next time. Thank you and goodbye.